Fifth day of chapter 5. We're working in section 5.3, and we're talking about inverse functions. Now, I'm hoping that everything that you see on the screen is a review for you from your days in either Algebra 2 or pre-calculus. So, just a little bit of a review as far as inverses. F of g of x and g of f of x. Inverses undo one another. So if they undo one another, then whatever g did, f would undo. So fx and g of x are inverses of each other. Domain of one is the range of the other. So that has to do with the fact that the point BA would be on the blue function, which I would call in this case my f of x, and AB then would be its partner value. That would be on the inverse function of x. So the red one and the blue one, I would say, according to the graph, are inverses of each other. Inverses are symmetric about the line y equals x. So the line y equals x is that purple dotted line that you can see on the screen. So wherever one of them hits the graph, the other one will too, because those x and y coordinates have to effectively reverse because of this domain range idea. Function can only have an inverse if it's one-to-one. So a review of what a one-to-one function is. One-to-one function has to pass the horizontal line test. So when we talk about a function, it's got to pass the vertical line test. Well, if it's also one-to-one, it's got to pass the horizontal line test. So if I draw a horizontal line, it can only hit the function one time. Or the other way to check to see if a function is one-to-one is to check to see if it's always increasing or decreasing. We'll get into some examples of how to do that in a little bit. So let's look at that red one and that blue one. They're going to each pass both the vertical line test and the horizontal line test. So they're going to be functions, and they're going to be one-to-one. Therefore, they can have an inverse on those particular intervals. So getting to what we're trying to do here. So first one, show that these two functions are inverses of each other. So as I'm making a little bit of note on how I might do this, I will tell you, looking at the information that's up here above, I could do a few things here. I could do the f of g of x thing. I could start off, one option I would have is I could do f of g of x and g of f of x. That's one way I could figure it out. I could graph both of these and look for symmetry. Especially if I had a calculator available to me, I could graph it and have a look and see if we have symmetry. Or the third thing I would do, and this is usually how I'll do it, I could find the inverse of one of them and see if it matches. So I'm going to choose to do this third one right here. So I'm going to start to finding an inverse. So finding an inverse, just as a quick review, remember, in order to find the inverse, you've really got 3 steps going on. Okay, to find an inverse. Find an inverse. Step 1, swap your variables. Step 2, solve for y. Step 3, the domain and the range interchange. And I'll explain what that with a little bit better detail, what that means in a couple seconds. So I'm going to start with this g of x. Now I'm looking at it, first off, I'm only supposed to use the positive, or x is bigger than 0. So g of x is 9 minus x squared. So the first thing I should probably think about, if I was to graph 9 minus x squared, I'd be looking at the right half of a parabola. X's are bigger than 0. Right half of a parabola opening downward. So that is definitely a one-to-one function. It's going to pass the horizontal line test and the vertical line test. So it's definitely a one-to-one function. Now, if I knew off the top of my head what the square root of 9 minus x looked like as a graph, now maybe some of us do. Maybe we can go through and we can punch it in. If we can't, now that I know that on this interval for x being greater than 0, this thing is a one-to-one function, well, now I can go through my steps. So I'm going to start with g of x is equal to 9 minus x squared. I'm going to swap my variables. So when I swap my variables, I'm going to put x on this side. I'm going to put y on this side. So I'm swapping my variables. X is equal to 9 minus y squared. So now solve for y. What am I going to do? Well, I'm going to start by subtracting 9. I'm going to divide by a negative, which a lot of people will write as 9 minus x, or maybe I should not skip that step. That would make this negative x plus 9 is equal to y squared, or 9 minus x is equal to y squared. Well, now I'm going to have to take the square root. Well, as I go and I throw a square root in, in the middle of the problem, we know that we're going to need a plus or a minus on it. Well, if I need a plus or a minus on it, in order to get this y by itself, well, how do I know if I want the positive on the square root or if I want the negative on the square root of the 9 minus x? So I have the plus and I have the minus out in front of that. Well, this plus or minus the square root of 9 minus x, I can't have both. And the way that I know how this is going to work, because the red function up here had a domain of 0 to infinity, that means that when I come down here, that means I'm only going to want the range of this function to be 0 to infinity, which means I only want the positive on my square root because of that domain range idea. So when I talk about this step 3 right here, this domain range interchange, whatever the domain is of the original function, my range is going to be of my inverse function. So I'm going to actually go through and take this negative out because I don't want that negative on my square root anymore. So, and while we were at it, if we come up here and we look, my original function would have a range of, let's see, of negative infinity up to 9, which means when I come down here, the domain of my inverse function is going to be negative infinity to 9. So whatever the domain is of one function is the same thing as the range of the other. And when you look at that domain, it makes sense because, for example, 10 would not be in that domain. If I put 10 into that inverse function, into that square root, I would not be able to come up with a solution. So there's my inverse. And if, since those two things are inverses, I have proven that this is indeed true. Okay, so we'll go back and we look at the other page. What we got going here? Can these functions have an inverse? Well, I look at that first one. If I draw a horizontal line right there, it's going to fail horizontal line test. This function is not one-to-one, and therefore there's can't have an inverse. Y equals x cubed. Well, let's see. There's a couple things. If I knew what the graph looked like, which I do, y equals x cubed would have to look something like this, that speed curve that we like to refer to. This is definitely one-to-one. So this will have an inverse. So we've got a yes and inverse here. Y equals x squared. Looking at the graph, we know what that graph looks like. This thing's definitely not one-to-one. So we've got no inverse here, as it's written. Now, if we limited the domain, we could make that happen. If you looked at one half of that parabola or the other, you could make that go. Well, number 3, here's something else for people to think about. If you took the derivative of this equation, dy dx is equal to 3x squared. This derivative is always positive. If the derivative is always positive, that means that y is always increasing. If y is always increasing, that's another way that we can know that this thing's going to have an inverse. So when we go back and look at the previous page, one of the things we looked at on part B, is this function always increasing or decreasing? Well, if your derivative is always going to have the same sign, your function is always going to be increasing. So you've got the black way if you know the graph, or if you can make the graph to check on this, or you've got the red way that you can use if you don't know about the graph. So here, if I look at number 4 to contrast, that derivative is going to be 2x. This is both positive and negative. That's both positive and negative. Can't have an inverse, depending on the x value that I plug in. Again, if you looked at part of the domain, it would work. And then this last one, find the inverse. We've already gone through what the steps are, so I'm going to go through and do this again. Before I start, we should probably think about what's going on with the domain and the range of this original function. Its domain, let's see, what can't x be? Well, let's see, 2x minus 3 has to be greater than or equal to 0. Or else I'm going to have imaginary numbers. So that means x has to be greater than or equal to, add 3, divide by 2, greater than or equal to 3 halves. So my domain starts at 3 halves and goes on to infinity. The range then, well, I'm looking at that thing, that square root has a positive on it, which means the range is going to start at 0 and go on to infinity. So that's what I know about my original function. Now to find the inverse, I'm going to swap my variables. X is equal to the square root of 2y minus 3. And I'm going to solve for my y. So let's square both sides. So I've got x squared is equal to 2y minus 3. Let's add 3. So y is going to be 1/2 of the quantity x squared plus 3. And if we want to know what the domain and the range are for that one, the domain would be 0 to infinity, and the range would be 3/2 to infinity, which would make sense because if I plug 0 in there, I'd get a y value of 3/2. And I'm only supposed to use half of this parabola over here that I just found for inverse because of the domain that was chosen for the original function. So here's my inverse along with its domain and its range.